Hello, I welcome you all. The problem reads, determine the horizontal force P that must be applied perpendicular to the handle of the lever at A in order to develop a compressive force of 12 kilonewtons on the material. Each single square threaded screw has a mean diameter of 25 millimeters and a lead of 7.5 millimeters. The coefficient of static friction at all contacting surfaces of the wedges is mu s equal to 0.2, and the coefficient of static friction at a screw is mu prime s equal to 0.15. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So we have been asked to find the horizontal force P. So let's look at just P here, what P is, okay? So imagine we have a coordinate system like this. Let me draw a coordinate system that we're going to refer to. So imagine we have a coordinate system like this. This is our Z, positive, this is our Y, positive, and this is our X. So if that is our X, then we expect a force in that direction, right? On the handle, all right? So let's call this is our P, okay? Let me make my line a little bit better. So we have our arrow like that. So this is the value of P we want, okay? And if we were to apply a moment in that direction, okay, so this is a force according to our coordinate system, is a force in the X direction, okay? And if we were to apply this particular force, we expect a moment about this threaded board, which will be in this direction. Let me write it here. It will be in this direction and it will be going like so, okay? So this is the moment that we expect, right? Okay, so expect this moment in this direction. And when you look at the threads, the way they are arranged in the opposite direction, so that we have this effect either taking the blocks this side, and when the blocks are moving in this direction like this, then it means they are applying a compressive force on the material. And if they are moving away like this, it means they are releasing or reducing the compressive force, right? All right, so we want this force, and this is what we want to do. So we'll need to dismantle the whole system, okay? These all blocks and all these wedges. We have two wedges at the bottom, wedge wedge B and wedge C. I'll call this C. All right, so let's dismantle all this so that we look at what is exactly happening. At the moment, we are saying we want to find the force P that will allow us to develop a compressive force of 12 kilonewtons. Okay, so let's dismantle this and then apply the reaction forces. Mind you, all these contacting surfaces here, this surface here and at the bottom here, okay, we've been told the friction is 0.2, all right? And then the friction between, because when you look at the wedge at C, this wedge at C also is acting as some kind of a nut, right? A nut, right? It has some, is it grooves or some threads also? So it has some where the threaded board is supposed to go through, right? So this is a nut, you know what a nut is, okay? And then you have a botted thread, a threaded board that is going through. So there is going to be friction between this nut and this this threaded board. The same thing with this nut at B. This nut at B also is going to experience friction between this threaded board and the nut. And for us to counter this friction, we need a certain amount of force that will create a moment about the centroid of this threaded board, so that we expect these particular wedges to move in the direction that we want them to move. Okay, so we are always, when these wedges are moving, we are overcoming friction due to this moment that is being produced by this particular force. So this force is directly proportional to this moment, right? So we know that M divided by R is equal to this force P times the lever distance, if this is our D, okay, times D divided by R. Okay, so this is the relationship. All right. So then let's go to the next page quickly so that we write the reaction forces. All right, here we are. So we've been told on this particular material, we expect a compressive force of 12,000. So this is how the material will look if we are to separate it. So it has 12,000 newtons or 12 kilonewtons. Okay. All right. And then on this top here, we are also going to expect some reaction force. All right. We expect some reaction force here of equal magnitude. All right. Then on the sides of this rigid material, let me start with wedge B. Wedge B, since wedge B, we expect this wedge to be moving in this direction, right? As we apply a moment about the centroid of the bolted threaded board. So we expect it to move to the right, okay? So we have this wedge moving to the right. We have this wedge on the right moving to the left. And as this is happening, then this block, okay, this triangular block is moving up, okay, applying some compressive stress, okay, or some compressive force. So there's also another material on top here which is just rigid, okay. So as this triangular block moves up, that material also is kind of applying some reaction force on the material. All right, so this is basically what is happening. So as this wedge moves to the right, we expect some friction force here to resist this movement, right? Okay, and we are calling this as our F. Okay, is that fine? And also we expect some normal force, that we are calling N. Okay, and also at the bottom here of B, we are also going to expect some other reaction force in this manner, okay, because they are both resisting this motion to the right. So I'll call this as my F star, okay, and I'll have also some reaction force, some normal force at the bottom here that we are calling N star. And in like manner also here I will expect the same normal force like so, and some friction force like that. And also on the other side there, the block is just more or less symmetrical, it's the same, so we expect similar reactions on the other side like so. I've not drawn the other block there, block C, because it is the same like block B. And then on this rod here that I've cut, this a threaded board, we are going to expect some axial force in it, right? Okay, so the direction that we assume again is not is up. Even when you make a mistake, your calculations are going to correct you, but you are not supposed to make mistakes on the direction of the friction forces. But for the axial forces in here, I know to say this is going to undergo some tension, okay, but even be it you made a mistake, then it's still fine. So I'll call this as my W. All right, deliberately I've given it W so that it matches with the model that we are going to draw. Okay, we've not been given the weights of these particular blocks. Okay, the weight of the block C and the weight of block D. I mean block B. Okay, so this one was C. There's a block C there, and therefore I think I'll call this not C. I'll call it rather D. Okay, sorry about that. I'll call it D. So block B and D, and block B and D are the same. Hence I just pick B. So we have all the forces. We have represented all the forces. We've not been given the weight of C. We've not been given the weight of B. We've not been given the weight of the material. All right. So with this information, let's look at the unknowns so that we know what exactly we are dealing with. So we have N, we have F, then we have N star, we have F star. Okay, what else? And then we have W, W, and then we also have P. Okay, I know it's not being shown here, but it's the one that is going to cause a moment about our threaded board. So we have 6 unknowns and how many equations of equilibrium? Okay, we can only take summation of forces and no moments. Okay, so we only have 4 equations of equilibrium, therefore we need 2 extra equations. And it just makes sense because these wedges are going to be moving. It means if they are moving, all right, or they are going to experience impending motion, okay, so we expect these to be governed by this particular equation. So we are going to invoke the friction equation, one of which is F is going to be equal to the maximum friction force at the boundary, which is mu S n, and then F star also is going to be equal to mu S n star. Okay, they've got the same friction coefficient, coefficient of friction. Okay, so having said that, then let's quickly apply the equations of equilibrium so that we find the equation plus the extra ones and then solve for their unknowns. So there we go, summation of forces in the y equal to 0 as usual. Okay, what do we have? We have minus 12,000. So we are on free body diagram BA. This I'll call it A, then this one I'll call it B. So minus 12,000, then minus, okay, since F and H, mind you, this angle here, this angle here, this angle here, this angle here is 15 degrees. Therefore, we have a 15 there. Okay, we are going to have a 15 there, and so is also there. Okay, 15 there. And I'll not write all the components because it will mess up my work. So I'll need some components of this. All right. So there we go. So minus 12,000, I've converted to newtons. Initially it was 12 kilonewtons, so I just converted to newtons. Minus 12,000, then minus, we have two F's that will have the same value. And I'm on free body diagram A. F will have two F's and they are both negative. So sine 15, and then plus N will have also 2, they are positive, and that's 2n cos 15 degrees equal to 0. Okay, and then what else? We have we go to free body diagram B. So there we have minus n, just single, cos 15 degrees, then plus F, okay, and sine 15 degrees plus n n star, okay, equal to 0. So we are done with summation of forces for both free body diagram. Then summation of forces in the x equal to 0. Okay, something like that. So what do we have? For block number A, if we are to sum up all the equations in the x direction, they just gives us 0. They cancel each other, so there's no need for free body diagram A. We go to free body diagram B. Free body diagram B, what does it give us? It gives us a minus f cos 15 degrees, then minus n sine 15 degrees, and then we have a plus w, okay, then we have a minus f star equal to 0. Great. And then we have these other equations that we just invoked, okay, mu s n f, which is equal to 0.2, that's the coefficient of static friction between all boundaries, times n. Then f star also is equal to mu s n star, which is just basically 0.2 n star. Okay, so with this information, what we are going to do is we are going to calculate the value of n. We'll get this value. Let's get this value. We have this f that we can replace here. So if we replace this f, if we replaced it in there, you can find the value of n, and n is going to be equal to 6563.3880. Okay, all right. So found what what n is, and since we know what n is, we can also replace this n here to just find f, right? Okay, if we did so, then we'll find that our f, if we multiply this n by 0.2, we'll find that we'll have f equal to 1312.6776. All these are newtons. Okay, so I'll write the units later on. Okay, so now we found f and n, so we can replace n there and we can replace f there, right? And if we did so, then we're going to have n star. If we calculated n star, because we have n and f in this equation, we are doing this equation there, then we are going to find that our n star is equal to 6,000. Okay, and if we replaced this n, we replaced it here, okay, then we'll find that our f star also can be calculated, because we are just multiplying this n by 0.2, and this gives us a 1200. All right, so after doing all this, then we'll come to this equation. We'll replace f there and n and f star. All right, and if we did this using this equation, make w subject to a formula, we'll find that our w and the direction we assumed was correct, and is giving us a 4166.6790. Okay, so we have found what we need. So what we are going to do now is to try and draw the model. Before we draw the model, we need to draw the unwound, okay, a thread, one revolution thread, okay, that we unwind from this threaded board so that we find the lead angle. So there we go. It is going to look like this, okay. This is a triangle, right angle triangle, looking like that. It's a thread. So we have this angle there, we are calling the lead angle, and then we have this one there, which is the L, and then we have this whole length, okay, this whole length, which is just a 2 pi r. All right, and then we have L given as 7.5 millimeters. We have D given as 25 millimeters, and we have R, which we can calculate, which is just a 12.5 millimeters. Okay, so with this information, we can go ahead and do our calculations. So we'll find that we know that tan theta, theta being the lead angle, is going to be equal to L divided by 2 pi r. And replacing these values there, we know that L is given as 7.5 divided by 2 pi times r, which is a 12.5 millimeters. And making theta subject of the formula, we'll find that our theta is 5.45 degrees. And then we also know that tan phi being the coefficient angle, I mean the friction angle, sorry, the friction angle is equal to mu, which is equal to 0.15. And making phi subject to a formula, we'll find that this angle is just 8.53. So with all this information, we can now draw our model so that we replace all the information so far that we've calculated. But before we draw the model, I also want to make mention of what is happening right now. Okay, so it means we've only found one W, but there is also going to be another W and D that we need to overcome using this moment that we want to calculate. This moment later on will give us T. So it means we are going to have two W's to counter the friction in the two screws stroke nuts, all right, because these screws are in contact with the nuts, and this is where the friction forces are taking place, and we need to overcome these forces using this particular moment that I'm just showing right now in green. Okay, so we have friction at block B, okay, because this block B is acting like a nut, and within this nut we have this threaded board that is supposed to go through as we apply a moment. All right, so we have friction at B and friction at D, and we need to overcome both of these using this particular moment, and therefore we are going to have two W's that we want to overcome. All right, is that fine? So in my model, I'll show two W's that I've just explained. So let's draw our model. So our model will look like something like this. Just a simple model that you've seen many times I've drawn. Okay, I think that's about it. Okay, so there we go. So let me extend this line here. So I'm able to show this angle here, which is the lead angle. And then on top of this particular threaded board, okay, or thread, because the thread is bearing all this load, we have what is called our 2W, okay, and I mentioned where this 2W is coming from, and we need to overcome it okay, by finding the moment that is acting about the centroid of the threaded bolt, right? And that moment is created when we are apply a force, okay, at the handle. All right, we said this M divided by R, M being the moment on the thread about the centroid of the threaded board, divided by R is the radius of the thread. Okay, so they say this is equal to FD times R, right? Okay, so we are applying a load and we want a compressive force on this material of 12,000 newtons. So it's like we are supposed to, it's like we are jacking something upward. Imagine what we are doing right now. We are jacking a vehicle up. We want to remove something. So it means the jack is going to bear the weight. So basically it means we are lifting the thread uphill, something like that. Imagine we are lifting something upwards. This is what this model is all about here. So it means we need a force in this direction that we are going to call M divided by R. Okay. So if we are pushing this particular block, imagine this block, we are pushing it uphill, then we are going to, it's just normal for us to experience some friction in that direction. Okay. And hence also having some normal force like so. Okay. Okay. And also we can represent the two forces, the friction and the normal force, by just one single force we are calling the resultant R. Okay, with an angle here between the normal and the resultant we are calling phi, which we calculated, which is just the angle of static friction. All right, and then also this distance here, this one here, we can represent it by this angle here, just using simple trigonometry. This also is theta, and therefore this whole angle there from the vertical to R, we can call it as phi plus theta. Is that fine? So with this information, it means we can be able to rewrite R, because our coordinate system is just in this direction like this. We have X and we have Y. So if this is the case, then it means we are able to find a component of R like so in this direction. Maybe this is too long, it's consuming my space. Okay, so this one is going to be equal to R sine phi plus theta. Okay, and also we have another one which will just be in this direction like this. Okay, this one, and this one will just be R cos. This is R cos phi plus theta. All right. So with this information, then quickly we can start doing our calculations. Let's apply the equations of equilibrium. So we have summation of forces in the x direction. Okay. What do we have? We have the following. We have m divided by r minus r sine phi plus theta equal to 0. And then we have summation of forces in the y equal to 0. Okay, what do we have? We have minus 2w, okay, then plus r cos phi plus theta equal to 0. Solving these two equations by dividing sine and cos, we are going to have just tan phi plus theta equal to, dividing the two, this just becomes m divided by 2rw. Okay, and we know that our m is equal to fd, which is just basically equal to, yes, the force times the d is the 250, or the 0.25 if we converted it to meters. So therefore we'll have tan equal to phi is Phi, we calculated it as 8.53 plus theta. Theta is 5.45. So phi is 8.53 and theta is 5.45. This is equal to m. We are saying, so let me create a small boundary here. I just create a small boundary so that we don't disturb what we're doing. So equal to what is our m? So we'll say m times point. We are converting this. We are converting the lever arm from 250 to 0.25, so that we convert it to meters, right? Divided by 2 times point. Converting 12.5 millimeters is 0.0125, right? Of course it is. 12.5 is 0.0125, and then we have W. What's W? W, we calculated it as 4166.6790. So we have an expression like this, and if we made f subject to the formula, we are going to have f equal to 103.73 newtons. Alright, this is about it, and this is the final solution, and this is the F that we need to apply so that we have a compressive force of 12,000 newtons on the material. I hope the video was helpful, and if it was, give me a thumbs up, continue subscribing, sharing my video, and liking my videos. Bye bye, and I'll see you in my next screencast.